go out to this end here, right? You see it's not like going out in either direction. It's going towards the target. Welcome back to Arcade. I am Super Tommy, and in this video, we're going to look at A-star search algorithm for pathfinding. Now, in a previous video, we looked at breadth first search for pathfinding, and A-star search is going to build on our breadth first search algorithm. So if you want to find that video, and if you haven't seen it, be sure to go look at it, since our code here is going to build on top of that code. You can go to the Arcade YouTube channel at youtube.com/arcadehq. You go to our videos tab here, and we have this pathfinding with breadth first search video. You can check that out to see how we got to this breadth first search algorithm. And so A-star is very commonly and popularly used in games to have characters find a path from point A to point B. So now how A-star differs than breadth first search is that A-star will basically go in a more direct route without checking the entire board or most of the surrounding tiles to find a path. So when we left off in our breadth first search video, similar to this, we've adjusted the board a little bit. But so if we wanted to find a path here, it's going to go look expanding out until it finds it, and then it generates the path. So we're going to do a very similar thing, except with A-star, what you will see is that instead of expanding outwards with just going out this way, expanding forever, it'll just sort of go more direct to the target it wants to get to and not have to check a bunch of other tiles that are clearly too far away to be the right direction. So here is the Wikipedia page for A-star search algorithm, and we are going to use this pseudo-code to implement the algorithms. But we're going to base it on the breadth first search implementation that we already did in our previous video. So let's see, is there anything else? Yes, let's talk about how A-star actually works to have a more targeted path that it chooses. Now it does that by using cost. So let's say right now here we have costs that are all basically the same. So there's no different costs. Whether you go up or left or right or down doesn't really matter. With A-star, there's going to be a cost from where the start is to where the current checked cell is. So as A-star goes, it's going to check, let's say we get to this cell. It's going to use the cost that is at that cell from moving to it. So let's say you have swamp, or you have forest, or you have grass, and they can have different costs. So if you didn't want your units or your character to travel through a swamp, because it's harder to travel or for whatever reason, you could make the swamp have a higher cost than plain ground. And then your character will basically walk around the swamp or a puddle or an oil slick, whatever it might be. So with A-star, there's costs to walking over a tile. So that's one half of it. Then there's another cost that it calculates based on wherever the cell you're checking is to where the target is. So it's going to pick the shortest distance as the next cell to go to. And by doing that is how it generates a more targeted approach, and it uses a priority queue instead of a queue. So when it does search, or when it does process the cells, it does it in a order of closest to the target. So when we implement this, it'll make even more sense than just me describing it. So let's go back here to Wikipedia. So in these algorithm pseudocodes or descriptions, we always have these mathematical functions or mathematical notations. And so, I mean, maybe you're good at reading this, but I'm terrible at reading f of g of h and all that stuff. So I try to, when I write it in the code, use some more meaningful names. But we'll try to parse this pseudocode as best as we can here. Okay, so this is their path construction method, function, and we have ours down here. If you looked at the breadth first search video, it's the same thing. you can see it's basically the same. And so we're going to leave that as is, so we can ignore this. So this is the actual A star function that they have. And we're just going to modify our breadth first search implementation to take costs into account and use a priority queue. So first, let's change our queue to priority queue. Now JavaScript does not come with a standard priority queue, but we've implemented a very simple one right here, right? So we've made our own priority queue. This is not even the most efficient priority queue. It is a very simple one. All it really does is when you end queue, you give it a priority, and it's going to go look through the entire list and slot in your new element based on the priority. So this is not the most efficient priority queue, but it works for this demo and it's quicker to write. Now you can also look for a priority queue library on GitHub somewhere, but I didn't find any that were fantastic, so I just wrote this very simple one. Okay, so we're going to change our queue to a priority queue. So new priority queue. Now, a priority queue basically will order the queue in order of priority. That's what it's called. A queue, normally you insert it into the queue, first element in, next element. They're ordered exactly how they came in. With a priority queue, if given a different priority, it'll sort them by that priority. So whenever you dequeue, you always get the lowest or the highest priority, however you want to look at it. Okay, so that's a priority queue. So let's see, we have open set, so priority queue, parent for cell, we're going to leave that. So now we need some costs. So let's just create some costs. We're going to store the costs. So we're going to do a cost from start. If you remember, we said we were going to have to measure the cost from where the start is, where the player is, let's say, or the unit is, to wherever the cell is. And then we're going to do a cost to target, which is the cost from wherever your cell is to the target. Cost to target. So now we're going to fill data in as we go. Okay. So now first thing, cost from start. Start key is going to be 0. So the cost from start to itself is, of course, 0 because we're already there. Okay, now our queue no longer has push. Since we are not using a list, we have queue, and then we want our priority. Our start position priority will be 0. And so we want to, let's go back here. Our while is open set is not empty. So in our case, when the queue is not empty, so queue dot is empty, not. So when the queue is not empty, we're going to go into this while, and then queue dot dequeue instead of shift. And let's see, let's just go and do the queue so that we can get rid of the old queue code enqueue. But actually, we don't actually know what the priority is, so let's just leave that. We'll go back here. So we have to queue this with a priority. So let's just go from here. All right, let's see what we got. So in this pseudocode, so they set the start to the open set, which is what we do in our queue. We add start. Then came from is basically our parent for cell. That's how we're going to reconstruct the path later. Now G-score. So G-score here is the score from start to where the cell is. So that's our cost from start. They call it G-score, and they fill it with infinity. But we don't have to do that. Obviously, filling an empty map with all the known keys is not actually necessary, since we won't actually touch every cell. So we're going to do it slightly more efficiently by only filling it as we need it. And then they put their custom start, G-score start is 0. Now F-score is the G-score plus a heuristic, that's the HN. So I'll just talk about heuristic. Heuristic is how we're going to calculate from the cell to the target, how we're going to calculate this distance. So there's the distance formula, which is a squared plus b squared equals c squared, and that's how you get distance from 2 points. Or you can use what is known as the Manhattan distance or the taxi cab geometry. I think it is somewhere here, it says Manhattan distance, right? Based on how taxi cabs can travel from point A to point B in New York City, you have to go up and over each block to get to wherever you want to go. So we're going to actually do both and show you how the outcome is a little bit different depending on which heuristic or distance algorithm you use. All right, so we're going to first, back here. So this is the F-score. So F-score is this, cost to target, and they have a start here, but I don't think we actually need that, so we're just going to ignore that. We'll see if we go back. If we do need it, we'll put it back in there. So let's go back here. So current, so this is all very similar to breadth first search. Now this is the...
Uh-oh, there's a problem. Please try again.
Okay, that was Siri. Now we're going to go through each neighbor. So in our case, our neighbors are going to be top, left, right, and bottom, just like breadth first search. And then for each neighbor, we're going to do this code here, which is going to create a score. So we're doing this check in case our neighbors go out of bounds, and it's right here. All right, so here we go. Let's do a cost. So the cost, as they have it here, is going to be G-score of current plus D, weight of the edge from current to neighbor. Okay, so G-score of current, so we want cost from start of current. So current is not key. Key is the neighbor's key, right? We're going through each neighbor. Current is the node from which we generated our neighbors. So in this case, when we first start, current is this red square. The neighbors is this guy, this guy, this guy, and this guy. Let's just clear this out. Current, start, neighbor, 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 neighbor. So neighbor north, neighbor east, neighbor west, neighbor south. Now for each one of those neighbors, we're going to do this. And so here, current key is our current. So that's G-score of current, or what is the cost from start of the current cell, plus the cost of the neighbor cell. And what we have is we created this matching grid. So this is the grid from the previous video that generates this map. And then we have a mirrored grid that gives you the associated costs of each a cell. So we're going to actually just make this back. So we'll show you later how changing this cost will make the algorithm do something different. So now basically everything is 1. We just say everything is 1. So every cost from going from one cell to the other cell is going to be 1. Let's go back here. So what we're going to do is add from our costs grid the neighbor's cost. So n row, n column. So that's neighbor row, neighbor column. So there is the cost. All right, next. So next, if the tentative G-score, which in our case is cost, is less than the neighbor G-score. Now, if you remember, we didn't fill our cost from start map with all the values. So what we're going to do instead is if, let's see, if key in cost from start, so if we're not in, if we don't have a value, right? So like checking against infinity would be the same as not having a value, since infinity would be bigger than any other cost value. Or cost is less than cost from start, key. So the difference between what we're doing and what this algorithm pseudocode does is it's assuming G-score has a value for every single neighbor, and we're saying we don't need to do that. We can just check that if there is no neighbor inside this cost from start, that it is as good as being infinity to check against. Okay, so next, now we're in this if. We are probably going to not need this, so let's just, we're going to comment this, right? Some of this is going to go back in here. So first we have came from, which is actually our parent for cell, right? So basically we're saying that the parent, if this is true, if this cost is less than the current cost, less than the cost from start of the neighbor, we will, oh no, of neighbor, no, that's right. Okay, we're going to put in the parent for cell so that we can later reconstruct a path based on figuring out the child's parent and then create the path from there. So that's what this is. And then we're going to do G-score. So in our case, it's cost from start. The neighbor, which is the key, gets the cost. Okay. So now we're going to calculate F-score. Now F-score was the score from the wherever the cell is, where the neighbor is, to the target. And we're going to use Manhattan distance for this first. So let's see. So we're going to call this, what should we call this? We'll just call this total cost. That's almost correct. Cost plus some distance. And so let's just calculate Manhattan distance step by step here. So we're going to call this dr for distance row. And what we're going to do is math.absolute value, the target row, that's the target, minus the current row, n row. So if we're, whatever this is, -1, let's say this is 3, no, 1, 2, 3, 4, 5. 5, this is 4, and so, and we're targeting here, let's say, so 1, 2, so 2 minus 4, it will be -2 or +2 absolute value, so it's always going to be positive. And then DC will be the difference in column, so tcol minus ncol. And then to get the distance, Manhattan distance, is just dr plus dc. And then we add that here. Now that is the F-score value as this pseudocode denotes. So now we're going to put it in cost to target. That is our F-score for the neighbor, total cost. Right, so our heuristic is this plus H neighbor. Our heuristic is currently Manhattan distance or taxicab geometry. And then, so it does a check here if the neighbor is not in the queue. Now, I also don't think that's necessary. So we're going to do q.enqueue. So some of this we're doing over, right? This thing, this, okay. q.enqueue, the neighbor, which in our case is neighbors I. And the priority in this case is going to be total cost. We're going to rank our neighbors that we queue up by their total cost that we just calculated here. And let's just put this await back in so that when we run this, you can see it working. Okay, so we shouldn't need any of this. Delete that. Okay, so here it is. Now let's see if we missed anything that looks like the algorithm built on top of breadth first search. So now let's just try it and see if it actually works. Let's just pick something easy, and it does not work. Q.Q. Where do I have Q.Q? Q.NQ. Q.Q. Q. Oh, right. Q.NQ. All right. Another error. Cannot read undefined of undefined. Let's see. Main 136 cells. Cells row column. Oh, yes. Dot element. So our priority queue stores, please save, okay. Our priority queue stores queue elements. When you enqueue something, you give it an element you want to enqueue. It wraps it in a queue element with a priority. That's how it does that's how it pairs a priority with an element. All right, back here. Let's try this again. And there we go. So there it is. You see it should have looked different than our breadth first search. So just go out to this end here. Right, you see it's not like going out in either direction. It's going towards the target. We'll do this one. As you can see, it's going more towards the target. So that is with Manhattan distance. So now let's look at it with normal distance or Euclidean distance, which is the a squared plus b squared equals c squared. So all we need to do is square this. We don't actually have to square root it. It shouldn't matter. As long as we compare the squared distance, it'll be the same. This is a trick we use in games to avoid having to do square root. Well, as long as you're comparing distance squared in all places, it should work fine. So let's go to this corner. And there we go. Let's go to this corner. And you see it's a little bit different. Let's do this one. You can probably see it better. Yeah. So with the taxicab geometry or Manhattan distance, you saw that it sort of expanded more in like a out to the west and south more. And with Euclidean distance, it's more targeted and more direct to the target. Now, so we have this cost stuff in place. Now let's see how it goes if we're going to put into our grid here, let's say some grasslands with different costs. Because you can have rivers in your game that, I guess there could be walls, but if your characters are much slower walking across water, let's say you would want them to avoid that. So let's say we do 3. So now we've pre-selected 3 to denote grass. You see, okay, so this green is going to be grass, and then we're going to give them a cost. So let's just say 9. You can play with these numbers. There's no right numbers necessarily. It just depends on the effect you want to have and what else is sort of around. Okay, so we have that. So now we set the costs and we set these grass in the way. So these are not walls, right? The walls it'll never walk through. So you'll see, because it's 9 though, that it's not going to walk through them either. So let's just pick this spot right here. No, it did walk through. Did I? Let's see. Hold on. Let's see. Did I miss a step? There's cost. Cost is not. Let's just try this over here. It does seem to be ignoring. Oh no, it is going through. Okay, yeah. Yes, the blue thing overriding is not a big deal. So it did deem. So let's just go back here. It did deem that going around would cost more than just going through the grass. Now, because we're using distance squared, would that make a difference? Not sure. Let's just make this bigger. You can do the math, but let's just make this like for sure that it's going to go around here. Let's see, 100. All right, let's just go big. That it definitely will not. So we set the cost to be high. So let's just do that. And it's going to go around because the cost was much higher going through than going around. Now let's change that. Well, no, let's make that 100. So now let's show you a case where, let's say we put slightly less tough grass. Let's say this is a short grass or whatever it might be. And in that case, short grass can be, let's just say that's 10. It's 10 times easier to walk across. And so do that. You'll see A star is going to just go through it because going around it costs more than going through it. Now if we go this way, I think still going around. Yep. Let's try this one. Going around. Let's try this one. And in this case, it was easier to go around the top than to go through the grass. Now, so that's basically A star search algorithm. It is the most commonly used pathfinding algorithm in games because it is targeted, it is faster than breadth first search, and that it searches less things. You can see that it'll just get there and it'll get there pretty fast. And you have the added bonus of costs for you to specify parts of your game world that could be cliffs, mountains, swamps, or other enemies. You could have characters that want to avoid where enemies are, or something like that, and then it'll walk around it instead. So A star is way more suited for games for pathfinding than just breadth first search. So if you enjoyed this video, do subscribe and let me know in the comments below what other algorithm videos you would like to see. Thanks for watching.